Hey everyone, welcome to the video on the volumes of similar cross-section. And these are a little bit different than the volumes of the solids of revolution that we've been looking at because we're not actually revolving anything. We're going to be building up from a base using a similar shape uh, for a lot of slices. So one thing that you can take a look at is like a pyramid, can be sliced at any height, and usually those will be a square if you're thinking of like the pyramids in Egypt. Um, but it's a bigger square at the bottom, a smaller square at the top if you do kind of horizontal slices. That's the idea behind these cross sections, is that I can slice an object and every cross section looks the same in terms of shape, but the scale may be different. So maybe some bigger, some smaller, but they're basically all the same type of shape, either a square or a circle or a rectangle that's equivalent, that type of stuff. Um, so the first one we're going to look at is this one from your kit. So the base region is bounded by these two equations. Y is 1/3 x plus 6, which is going to be this top line that's right here in the graph, and y is 1/9 x squared, which is this bottom line in the graph right there. And the cross sections that we're going to build are perpendicular to the x-axis, and they are squares. So you have kind of this white, opaque-ish, creamish colored object in your kit, and you may not have the squares already in there. You may have to take the squares from a baggie and put them in there. Um, but go ahead and take those out. Put those in the slots that you see, so you can lift this cover off and put those in the slots. And if you want to put the cover back on, you can kind of see the squares through there. But the idea is that what we're going to have are on this shape, all of these slices, right, are going to be perpendicular to the x-axis. So that would look like this on our shape, perpendicular to the x-axis. And you have to be careful when you read these. A lot of times they say perpendicular. Every now and then you'll run into one that says parallel, but you're just looking at, right, every slice that you're taking is going to be perpendicular to the x-axis. So in this case, they're all running vertical. And that is going to correspond on this shape to, just how those grooves are running in that object. And then what we're going to do is we're going to build up a square from that. So, of course, over here on the left, where you don't have quite as long of a groove, you're not going to have quite as tall of a height either. So that square is just going to be a small square. Whereas in the middle, where you have a much longer groove that you're slicing, that is going to be a much bigger square on that guy. So that square that goes up there is much taller from that one. And you can see that it's a much taller square right there in the middle. If you want to think of it going out this way, and then it goes down the bottom, we'll dash that in, like that. So, and you can have that, parabola shape there on the back side that you can't really see. But all of these shapes in here, if you draw it right, these should all be squares that get drawn in. So all these guides are going to be squares. And we're just building up all of those squares across that whole region, and that makes this solid object that you see with the top. So what we want to do is kind of look at what is the volume of just a sample slice, right? Before we were doing a sample slice was a disc or a washer or a shell. In this case, it's going to be whatever shape they tell us we're using, in this case, squares. We'll do some others in another video with a different shape. But just use that shape to find the volume of these sample slices and then add up all the slices across that whole interval of my region. So that's the idea. So with this, we're using squares. So let's think of, say, some of these squares like this that we got right there. And if you want to, draw them on this, you can kind of try to sketch those in as well. Sometimes it's a little bit hard and trying to draw 3D on these guys. But you can think about the thickness, right? What do we call the thickness of this square? Well, in this case, vertical rectangles, that's going to be a dx for the thickness. So that's this little thickness right here, dx. So it's right there. In this case, dx. Like I said, in other cases where maybe you're perpendicular to the y-axis or parallel to the x, you might have a dy, but this one we got a dx. How would I rewrite my base b so that it is in terms of x, since we're using a dx? So my base b, we'll just call this b right here. So that's the bottom side, is right from this y on top to this y on bottom. And we've done this stuff before when we were looking at area and centroids and all that. I just need the length of this rectangle that's right here. So my base is always this y on top minus the y on bottom. So in this case, let's say the top minus the y on bottom, and that's going to be that line, which was 1/3 x plus 6. Let's say 1/3 x plus 6, and then minus that y that's on the bottom, which is the parabola, 1/9 x squared. What's that, guys? So on bottom, 1/9 x squared. All right. And you can go ahead and rearrange, simplify if you want to. There's not much you can do here, but that b would just be, let's say, negative 1/9 x squared plus 1/3 x plus 6. So that would be the value for that b. The next part is going to be looking at what is the volume of this cross section, right? So we got the length of one of the sides, which was b. What is the volume of that? So if I think about this stuff in terms of b, I have a b on the bottom. This is a square, so we got a b going up on the side, and then this was my dx, right? So volume is going to be that length times width times height, so all three multiplied. So we get b times another b, so b squared. Not too surprising, area of that face, if it's a square, is going to be b squared, and then times that thickness, dx. And then you can rewrite that in terms of x when you want to actually do out the integral. So if we're going to do out the integral, this would be the integral of, and instead of b, I'll go and replace that with what we had before. So that was that negative 1/9 squared plus 1/3 x plus 6. Go back and double check that in a second. And that's my b, and that b is getting squared, right? So this is going to get squared, and then my dx, right? And when I plug in my bounds, right, so these are going to be x bounds. Let's go back and look at our shape. Looks like it was running -6 to 9 right there, those 2 points. So x is -6 to x is 9 on those. So we'll say -6 to 9, and that would be my volume, right? And then, of course, you can just plug that in and evaluate that on your calculator or on Desmos or something similar to that. So we'll go and calculate that out, see what we get. Alright, so here I've gone into Desmos and kind of calculated it two different ways. One is just putting what we simplified from our worksheet, the negative 1/9 x squared, 1/3 x plus 6. All of that, that's our b, so that whole thing squared. Evaluated -6 to 9, and I get 312.5. Another way you could do it is like put in, your y1, y2 for graphing. those equations. And then in place of my b, right, it's just that top minus the bottom. So in this case, the y1 minus y2 for the b, and that b is getting squared right there. And again, evaluated -6 to 9 for the x's. Same thing, 312.5 is what I get. So however you like to do it is fine. If you like to simplify first and then plug in, or if you just like to put stuff in terms of like a y1, y2 sort of thing, that will also work. Either way, we get 312.5. And we'll go ahead and come back over here and put that in. So 312.5. On some of the other shapes, it's going to be a little bit trickier, so I'll come back to this here in just a second. But so what if my shapes were, say, equilateral triangles or semicircles or some other type of shape other than a square? Some of the shapes are not too bad. Equilateral triangles can be a little tricky because the height is not the same as the base. You got to figure out what is the height of that triangle going to be. Semicircles aren't too bad, but the next video we'll kind of talk about a couple of these different shapes. What I want to end with on this one is just this last sort of thing right here. So as you work on some of the problems, it does help to kind of keep the three views in mind, what I call three views. This 3D cross-sectional view, right? So if I have the lines and then the squares coming out of the page, that sort of thing, where you can kind of visualize that in 3D of what those squares are doing. Bigger in the middle, getting smaller as you go down toward this small intersection down here at the end. Kind of the top-down view, right? So you can draw in those, rectangles that form the base, and to see what sort of values am I going to get for my b. That's my base. So that kind of top minus bottom thing, but I call that the top-down view because you're looking straight down on it, and all the slices, no matter what the shape, kind of look the same in the top-down view. It's just a rectangle across that base in between those lines. And then the third, this general cross-section use, and this is useful for thinking about, right, what is the volume of my general slice, whether it be a square, a triangle, a circle, a semicircle, anything like that. So just what is the volume of that general cross-section, so that I can add all these up. And it's usually nice to get these in terms of b, because b is typically just kind of the difference between a couple of curves here. So so those are the three views to keep in mind as you go through. Again, we'll do a couple more examples with different shapes in the next video.